Hello everybody and welcome to our next video in Unit 3, which is we're going to continue intermolecular forces. In this case, we're going to talk about hydrogen bonds. We'll talk most about hydrogen bonds, and we'll talk about the last two types of bonds as well, or the two types of intermolecular forces, where the last two should be relatively easy for us to look at. What I want to look at, though, is just a graph of a whole bunch of different covalent hydrides. So in this example, we have a whole bunch of those P block elements that are combined with hydrogen. And we could see some really nice trends that are happening here if we look really, really closely. Let's start out here at the bottom, because I think it's the easiest to point this one out. Notice how CH4, SiH3, germanium, and tin, all of these guys seem to have the lowest boiling points of the whole entire group. So right here, these have the lowest boiling point. Why would they be the lowest boiling point? If you consider their Lewis dot structures, methane is nonpolar. So is silicon tetrahydride, germanium tetrahydride, and tin tetrahydride. All of these are nonpolar. So because they're nonpolar, they have no dipoles. These experience only London dispersion, intermolecular forces of attraction, which we know are some of the weakest intermolecular forces. Granted, when we start to compare, we'll do some comparing. In that case, that's not entirely true, but in this case, we're going to call it true for this particular graph. Only London dispersion forces. And notice that as I add electrons, so silicon has more electrons than carbon, so the boiling point will be higher for SiH4 and even higher for germanium because that has more electrons, and then tin has even more electrons than the other ones. However, we start to see some anomalies right here. So notice, holy moly, right? Water has by far the highest boiling point of any other covalent hydride. And I know some of you guys that have taken AP Bio before, and some of you that have taken Chem 2, you might remember what's so special about water. Water has the ability to hydrogen bond, which is our next type of intermolecular force. And all three of these actually experience hydrogen bonds. Hydrogen bonds are the strongest type of intermolecular force that are present. Let's go ahead and look at some of these here. So notice how for water, right, super duper high boiling point, but for sulfur, who's right below oxygen, its boiling point goes down quite a bit. What's the primary intermolecular force between molecules of H2S? We start to see some dipole-dipole. I'll just write di-di. Very polar molecule, but not polar enough to hydrogen bond. As I go down the group, so selenium has more electrons, so therefore it has a more polarizable electron cloud. Stronger intermolecular forces in tellurium has even more electrons, so its boiling point will be higher. So notice how once I get rid of this hydrogen bond, we do start to see the trends between the groups. Why is hydrochloric acid, why does that have a lower boiling point than hydrogen sulfide? Like we said in the last video, hydrochloric acid is not as polar as hydrogen sulfide. And that's because hydrogen sulfide has two bonds, both of which are going in the same direction towards sulfur. If we remember back to this problem here, whereas this one has only one. So really nice way to show how these trends are affected by their location in the periodic table. And of course, as I go across the period trend, this is true for all of them because these have more electrons as I go across the period. More electrons, which means I have stronger London dispersion forces. Okay, so that's why here, or as I go down a period rather, or as I go across a period, but what period it's in. That's what I meant to say. So like nitrogen is in period 2, whereas phosphorus is in period 3 and arsenic's in period 4. So going down a group, but it's what period number. As I go down the group, adding more electrons, thus it makes those London dispersion forces stronger. What we're going to talk about in this video is your hydrogen bond right here. Hydrogen bonds are a pretty special intermolecular force of attraction. They are very, very specific. So your hydrogen bonds are permanent forces of attraction between a hydrogen that's bonded to an FO or N and an FO or N on another molecule, right? So, or we can also have another side of a very large molecule. So in this case, I have water. Water is a great example of a molecule that can hydrogen bond. So I have one water molecule, which you can see right here. Okay. Partial negative charge on oxygen, partial positive charge on hydrogen. This partial positive charge on a hydrogen is attracted to an oxygen on another nearby water molecule. This right here is the hydrogen bond. Hydrogen bond. Okay, didn't draw that very clear, but you get the idea. That's the force of attraction. Because oxygen is so electronegative, this type of force of attraction is stronger than a dipole-dipole. So this oxygen-hydrogen bond is more polar than an oxygen-sulfur bond. So this would have more electrons going towards oxygen, which is what makes these sort of just like really strong dipole-dipole intermolecular forces. But the criteria is I do have to have a hydrogen directly bonded to an FO or N, and that is attracted to an FO or N on another molecule. So we have to look at partial positives on one molecule is attracted to a partial negative on another molecule. Here's another example. Great examples with ammonia. So in this case, my partial negative would be on ammonia, and my hydrogens are partially positive. Your hydrogen bond is the force of attraction between the partial negative end on one molecule and the partial positive side of another molecule. Okay, that is the hydrogen bond, what it's pointing to right here. Notice this image. This bond is the intramolecular covalent bond. Notice it's with the solid line, whereas your dotted lines are your intermolecular hydrogen bonds. Okay, so please make sure you keep those clear. Your hydrogen bonds are the strongest of the intermolecular forces, but they are still very weak relative to your covalent bonds. So we do represent that with dotted lines. Rather than talk more about this, because I know you guys have seen this in AP Bio, and I know you've seen it in Chem 2, so I'm not going to stress too much on reviewing this, but let's just do some sample problems together. So consider the isomers of C2H6O. Isomers they have the same formula, but they have different structures. So both of these, dimethyl ether and ethanol, have the formula of C2H6O, but they have different connectivity. They have different structures. One has a boiling point of 78 degrees Celsius, and the other has a boiling point of negative 20 degrees Celsius. Match the boiling point to the structure and explain your reasoning. So if I look at both of these structures, let's draw some lone pairs in there first. One of these has the ability to hydrogen bond, and the other one does not. Okay. Ethanol has the ability to hydrogen bond. I have an oxygen directly bonded to an OH. This particular bond is a superpolar bond. Because that is a very polar bond, it will more strongly attract other nearby ethanol molecules. So ethanol has the higher boiling point of 78 degrees Celsius. whereas dimethyl ether has the negative 20 degrees Celsius boiling point. And this is because those ethanol molecules can hydrogen bonds to one another. Those hydrogen bonds are stronger than the dipole-dipole intermolecular forces that hold together dimethyl ether. You might be like, wait a minute, Mrs. Snyder, this looks nonpolar, right? We have to remember in real life, what's the shape about this molecule? This particular molecule is bent. So really, I have a lone pair coming out one end. I have a lone pair behind it. And then I'd have my CH3 groups coming out the side there. So this is a polar molecule. It's dipole-dipole. But this one can attract other nearby ethanol molecules much more readily because it can hydrogen bond. So let's insert a text box here because I don't want to confuse you even more with my handwriting. So we'll say here, ethanol has the ability to hydrogen bond, which means the molecules are more strongly attracted to one another. This means more energy is needed to break them, leading to a higher boiling point. Hydrogen bonds are stronger than your dipole-dipole, especially because these have the same number of electrons, right? And that's important. Because these have the same number of electrons, we are going to consider that the London dispersion forces do not affect this. Let's take a look at sample problem 4. Explain why the boiling point of ethylene glycol is even higher than the boiling point of ethanol. So ethanol, which is still up above, right, has a boiling point of 78. Notice ethylene glycol in its structure, right, has an even higher boiling point. It's actually double, over double the boiling point. Why does it take so much more energy to vaporize ethylene glycol than it does ethanol? Why do ethylene glycol molecules like each other so much that it takes a lot more energy to separate them into a gas? Well, that's because ethylene glycol can hydrogen bond not just once, but it can hydrogen bond twice. If I take a look at this structure, okay, we can in fact see I have a hydrogen bond here, or I can have another hydrogen bond here, and I can hydrogen bond here as well. So ethylene glycol has even more areas where we can hydrogen bond, which is why the boiling point is going to be even higher. So we'll say ethylene glycol has the ability to hydrogen bond twice at both. If you remember from AP Bio, what are those OH groups called? They're called hydroxyls. Making them even harder to separate and vaporize. There we go right there. All has to do with how many times can it hydrogen bond. If it can hydrogen bond more times, it's going to be stronger to break. You might remember in AP Bio, you talked about, or even in regular bio, what holds together the strands of DNA. They're hydrogen bonds. Guanine always bonds with cytosine because they have the same number of hydrogen bonds. And adenine always bonds with thymine because they have the same number of hydrogen bonds. That's why you're never going to have cytosine bonding with thymine, because their structures don't match up. And actually, cytosine and guanine can hydrogen bond 3 times, whereas adenine and thymine are 2 times to one another. So it takes a little bit more energy to separate cytosine and guanine. I don't know if you learned that in AP Bio, but there it is. So water is a liquid at room temperature, whereas paraffin is a solid at room temperature. This means that paraffin has a higher melting point despite water having the ability to hydrogen bond. Account for this discrepancy. So you might have heard me say already, hydrogen bonds are the strongest of the intermolecular forces, right? Which is only partly true, because we have to consider how many electrons something has as well. So even though water has the ability to hydrogen bond, water only has a total of 10 electrons, right? So let's go ahead and just draw 10 electrons here. Whereas paraffin, I don't even know how many it's got. It's got way more. Just write way more electrons. Okay, 6 times 30 is 180, plus another 62 gives us 142 or 242. 242 electrons. 242 electrons. Why is paraffin a solid even though it's nonpolar and it only exhibits those London dispersion, intermolecular forces of attraction? So let's go ahead and add a text box here. But those London dispersion forces start to get pretty strong when there's a lot of them, because paraffin has so many electrons. It's kind of hard to break it down even more than that. So we're going to say paraffin, font that I like first. Paraffin is a very large molecule with many electrons, which we said it's got 242 before. Therefore, the London dispersion forces between paraffin molecules are very strong relative to the hydrogen bonding in water having only 10 electrons total. So as I'm personally, when I'm trying to rank elements, when I'm trying to rank compounds based on boiling point, I tend to look at what type of intermolecular forces between them first. So I usually recognize, like, okay, this has the ability to hydrogen bond, which I know it's going to be pretty high. But then you have to also consider how many electrons do they have. So it's not necessarily just one thing that you're really concerned with. You have to look at the whole picture, not just the type of intermolecular force, but you also have to look at how many electrons they have. Let's talk about another intermolecular force right here. So another one that we didn't really talk about too much in Chem 2 was a dipole-induced dipole. So a dipole-induced dipole. I have a polar molecule, and it's basically forcing another molecule to become polar. Dipole-induced dipole is when a polar molecule forces a non-polar atom or molecule to temporarily become, and it's not technically becoming, I'll put become in parentheses, polar. Great example of this is when I have Italian salad dressing. Okay, so you have Italian salad dressing. It's got the oil, it's got the vinegar. Stay separated, right? That's because vinegar is a very polar molecule. Vinegar has oxygens in it. So let's put down here, vinegar would be the molecule that has the dipole, whereas the neutral molecule would be oil. They tend to separate. Like dissolves like. Vinegar and oil are not like one another. In fact, they are very unlike each other. And that's because they have different intermolecular forces. However, this vinegar can induce a dipole on oil, because if this is polar, right, this positively end side of vinegar can pull the electrons in oil closer to it, right? Which makes oil going to be polar for a very brief moment in time, hence temporarily become polar. How do we know it's temporary? Well, what happens when you shake it up? The Italian salad dressing stays together. But if you leave it for a little bit of time, it's going to separate again. right? So for that temporary time, those particles are attracted to one another. They stay together. They stay mixed. That vinegar induces that dipole on that oil, but then they will go back to how they were, back to being a dipole and a totally neutral molecule that really don't like each other. How do we get these to like each other? You might say, well, some salad dressings stay together. You can actually permanently induce a dipole in salad dressing by adding either honey or Dijon mustard. I learned that in my food chemistry class. Honey and Dijon mustard has both positive and negative sides, that it actually keeps them together for a longer period of time. So if you have some sort of salad dressing that you made at home, let's say, because sometimes I'll make salads at home and it's make your own dressing, and they won't separate if you add honey or Dijon mustard. So fun fact for you there. So then the last type of intermolecular force that we are going to talk about is a dipole-ion intermolecular force. Oops, oh gosh, I'm changing everything around over here. Okay, is a dipole-ion. And actually, this type of intermolecular force might actually be the strongest because we are actually starting to introduce an ion into this scenario. So a dipole-ion is an attractive force, that occurs between an ion and a polar molecule. And this is going to be very common in solutions. So if I make, for example, a salt solution, the force of attraction that holds those salt ions together next to those water molecules is a dipole-ion. Now, in fact, your dipole ions tend to be some of the strongest intermolecular forces. And sometimes you'll hear me say hydrogen bonding or London dispersion is the strongest. It all kind of depends. Dipole-ion might be the strongest when we talk about intermolecular forces, because when I consider ions, ions aren't necessarily considered molecular, right? They're ions. They're part of an ionic bond. So these ones are not as common as some of your other intermolecular forces, but you're only going to find these in solutions, really, because I typically take ionic substances that will dissociate in water, a very polar substance, and we produce things that look like this. So in this case, here is our water molecules, and they're all surrounding my sodium ion. Now notice that the sodium ion is surrounded by the oxygens of water. That's because my positively charged cation in the center is attracted to the negatively charged side of water molecules. That's why this is arranged in a certain way. The reason why these dipole ions are in fact a little bit stronger than your other types of intermolecular forces comes back to Coulomb's law, the magnitude of the charge. That sodium ion has a full-on positive charge. Whereas if I consider water molecules attracted to one another, they're only partial negatives or partial positives. If I have a full-on positive charge attracted to the partial negative sides of water in a solution, this is actually going to be a pretty difficult bond to break, these dipole ions. So let's use that and draw water molecules that are surrounding a chloride ion. So chloride ion is going to be, of course, negatively charged. So let's take my Cl-1. And I'm going to make this guy a little bit bigger. I made it a lot bigger, actually. Just because if I have chlorine that has gained an extra electron, nuclear charge can't pull in that additional electron as closely. So the ionic radius of chlorine is actually larger than that of sodium. If this has a negative charge, that means that the positive side of water molecules will attract the negatively charged chloride ions. So here, my hydrogens are going to be facing this chloride ion. Same thing going on the other side. And I'm not very good at drawing water molecules like this. So here we go. partial positive end of water is attracted to the negatively charged chloride ion. So let's draw one more here for good measure. There we go. Your force of attraction is right there in between. Same thing there. I wouldn't normally make them touch, and that's because it's not a bond, right? They're not actually touching. They're just attracted to one another. So if they're attracted to one another, they're just going to be near one another. Let's go ahead and make a quick summary here with this relative strength of intermolecular forces. So London dispersion forces are your weakest, and this is true for nonpolar molecules only. And that's because they have to have a temporary dipole, and that's because their electrons aren't totally centered around the nucleus, creates a partial negative and a partial positive side, but as soon as it happens, it goes away. So they are the weakest. Dipole-induced dipole. This occurs between a polar molecule and a nonpolar molecule. This is also a temporary dipole. Both of these are what we consider temporary. That's because they're there and then they break, right? Because they are so weak, they can be broken pretty easily. Great example of this one would be the oil and vinegar example. Dipole-dipole, hydrogen bonds, and dipole-ion. These are all permanent dipoles, which is why they're stronger. Permanent dipoles. This dipole-dipole occurs between all polar molecules. So notice how we go from nonpolar to polar and nonpolar, which is a little bit stronger, to all polar, whereas our hydrogen bonds are where we have those very specific qualifications. I have an H that's bonded to an F, O, or N, and that's attracted to a hydrogen on another nearby molecule. So in this case, it's still permanent, but these are like your superpolar. So I'll just write superpolar bonds that are associated there. Whereas your dipole-ion are your strongest, and that's because your ions have a full-on positive or negative charge. So these are a full positive or negative charge. Those are going to be stronger. Again, think about Coulomb's law, the magnitude of the charge. It's going to be much harder to break a bond between a full-on positive charge as opposed to just a partial positive charge. This particular comparison can only be used when the molar mass is about the same. We'll say molar mass or your number of electrons, really. If I'm comparing, for example, a very huge oil molecule to something like hydrofluoric acid, if I have a huge nonpolar oil molecule with 600 electrons versus if I have hydrofluoric acid with 10 electrons, sure, hydrofluoric acid can hydrogen bond, but that oil molecule has a ton of electrons, and those London dispersion forces become really strong when there's a lot of them. So we can really only use this particular ranking here when we're talking about compounds of similar number of electrons. And we're going to get lots of practice with that in class. So how do we differentiate? Where's the cutoff, right? Hopefully in class, we'll talk more about where that particular cutoff is. And overall, what you need to recognize is that your intermolecular forces are significantly weaker than your intramolecular bonds. So those hydrogen bonds, those dipole-dipole, those London dispersion, much, much, much weaker than those covalent bonds, those ionic bonds, and those metallic bonds. This is something that takes a lot of work. I tend to feel that my students get very good at intermolecular forces because we focus on it so much. A lot of your AP test will come back to intermolecular forces, so I make sure that you know these intermolecular forces very, very well come test time. As always, please let me know if you have any questions. We will practice this a lot in class, and I will see you in the next video, which I'm not sure what it's going to be on, but it'll be something in Unit 3. So I'll see you then. Bye.